Statistical significance. To start a significance test, a carefully worded hypothesis that expresses the hopes or suspicions needs to be written about a population, not just the sample, before seeing the data. Once the hypothesis is completed, the next step is to choose the appropriate test. There are various significance tests available, and the choice of test depends on the type of data obtained and the research question that is trying to be answered. More information about the tests are discussed in the next few topics. For now, let's focus on what happens after a test has been completed. Significance tests ask if the sample data attained either provides or doesn't provide convincing evidence against a null hypothesis. For now, we are going to skip over the test component to focus on the answer component. The answer to a significance test comes in the form of probability. How likely is it to get a particular result by chance? This is where that p-value comes in. The p-value measures the strength of evidence against the null hypothesis and indicates how likely it is that the observed differences or associations between the variables or groups are due to chance. In other words, it's the probability of obtaining a result as extreme or more extreme than the observed result, assuming the null hypothesis is true. After calculating the p-value through a significance test, it is compared to a given significance level, also known as alpha, and that's the Greek letter alpha, which is typically set at 0.05 or 5% or 1/100th or 1%. If the p-value is less than or equal to alpha, the null hypothesis is then rejected, and the alternative hypothesis is accepted, meaning that the observed differences or associations are statistically significant. For example, if the p-value we get from a test is 0.02 and the significance level is set at 0.05, then the null hypothesis would be rejected because the p-value is less than alpha. This means that there is a strong evidence against the null hypothesis and that the observed differences or associations are statistically significant. On the other hand, if the p-value is greater than the significance level alpha, the null hypothesis is not rejected, and the observed differences or associations are due to chance. Let's try an example. Your friend claims to have a 90% accuracy for free throws in the game of basketball. You don't believe them. To test this claim, they shoot 50 free throws and make 38 of them. What would be the null and alternative hypotheses in this case? Since your friend claims to have a 90% accuracy for free throws and you don't believe them, the null hypothesis would be that they actually do have a 90% accuracy for the free throws. It would prove you wrong. And then the alternative hypothesis would be that they would have a less than 90% chance. And this means your feeling was correct and your friend's accuracy is less than 90%. And this is called one-sided because we don't necessarily care about whether or not the accuracy is lower than what is claimed. Now that we have the null and alternative hypotheses, do we currently have enough evidence to reject the null hypothesis? Well, if we take the data that we had from our test, they shot 50 free throws and made 38 of them. And that's equivalent to 76/100ths or 76%. Now, this in the sample does show that they are incorrect. However, there are a couple of different explanations for this. Yes, we see that this is not equal to 90% and it's less, but we could have the null hypothesis be correct and just by chance a very unlikely outcome occurred. Your friend could be having a bad day and make a smaller percentage of free throws on that one day. The other option would be that the alternative hypothesis is correct and the sample result is not a chance of occurrence, meaning we are correct with that alternative hypothesis and the null hypothesis can be rejected. So which one is it? Well, this is where we would perform a significance test to see whether our null hypothesis is correct or our alternative hypothesis is correct. The observed statistic is that our sample proportion, p hat, is 76/100ths, or 76%. A simulation of 500 sets of 50 free throws with 90% accuracy is run through a software program. It finds that of the 500 sets, only 8 sets calculate the shooter at the observed 76/100ths, or 76%. So what is our p-value? Well, our p-value is calculated by taking the 8 sets out of the 500 that were done through the software program and dividing them. And when we do that, we will get 16 thousandths, or 1.6%. What conclusions can we draw from this? So the p-value that was found, which was 16 thousandths, or 1.6%, is so small that it provides sufficient evidence against the null hypothesis, which was that our friend has a 90% accuracy with free throws. So that means if our shooter does have that accuracy, the chance of only making 38 out of 50 free throws is extremely small, our 16 thousandths, or 1.6%. So the sample we observed is unlikely to be an uncommon occurrence. For this reason, we would reject the null hypothesis and be in favor of the alternative hypothesis, which was that our friend's accuracy is less than 90%, because we have enough evidence that the shooter's accuracy is well below the 90% desired.